Okay, good morning and welcome back to Math 115. So let's see, yesterday, what did we talk about? We talked about some exponent rules. We did a little bit of algebra with exponents, and we did some, right at the end there, we started talking about polynomials. We defined what a polynomial is, and we talked about how to add and subtract polynomials by combining like terms. So what we're going to do today is kind of continue down that path. We're going to talk more about polynomials. We're going to talk about how to factor polynomials. We're going to talk about how to multiply polynomials. And we're going to talk about, if we have time, we'll get to some discussion about rational expressions. So polynomial fractions, okay? So fractions where we have a polynomial on top, polynomial on bottom. Okay, so let me share the iPad screen. And we will jump right in. All right, great. So why don't we have really quickly a recap of what we did, and we'll do a little bit more adding and subtracting of polynomials. Okay, so let's get our bearings here. So we had all these rules about exponents. We learned how to deal with negative exponents. We learned how to deal with powers of x to another power. We learned how to distribute powers onto things which are being multiplied. And we did some practice. And we learned about the definition of a polynomial. We said it's a sum of powers of x with non-negative integer powers, such as x squared, x cubed minus 7x squared plus 2x plus 1, 3x to the 7th minus x plus 0.5. All these are good. In fact, I could even give you one more, and that would be the general definition of a polynomial. This is how we write it. We write an x to the n, where n is some Let's try that. Can you guys hear me now? Okay, for some reason I can see the chat in the meeting, but I can't see. Oh, there we go. Okay, everyone can hear me now, right? Okay, wonderful. Man, that was unusual. Okay, so I think where I left off was I was trying to give you the general form of what a polynomial looks like. Sometimes we write an x to the n, where n is some presumed to be some positive integer, and then we'll write plus, and we'll write a n minus 1 x to the power n minus 1 plus dot 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 plus a2 x squared plus a1 x to the power 1 plus a0. And this is how we'll generally write it, and we'll call this guy the leading term. And we'll call this an. We will call that the leading coefficient. And we will call this power n, the largest power n. We will call that the degree. We'll also call this last term, we will call that the constant term, or constant coefficient. Okay, so that's kind of how we write polynomials in a really general way. Okay, so we talked about adding polynomials, and we talked about combining like terms. We said we just need to find terms of the subtraction or addition which have like degree powers of x, and combine those terms. So let's try one more. We'll do x cubed minus 21. We'll take that polynomial and we will subtract 2x cubed plus x plus 3. Okay, so let's try this one. So all we have to do is find the terms which have like degree and combine those. And remember, I need to distribute this minus sign here onto each of these 3 terms here. Okay, so first of all, I could kind of rewrite this whole thing by dropping the parentheses on the first one. And then we will subtract 2x cubed, subtract x, and subtract 3. Okay, so I need to remember that if I have a minus sign in parentheses in Pemdas, remember Pemdas, we always do parentheses first, so we should distribute this minus sign onto everything that's inside the parentheses. So we'll do that, and then we'll just combine like terms. So we look for anything with a cube, and we'll combine those. So we've got x cubed minus 2x cubed. That's going to give me negative x cubed. And we're going to look for anything with an x, just the 1 minus x. So we'll have minus x. And we'll look for anything with a constant and no powers of x, and we'll do minus 24. Okay, so that's how we combine like terms and add and subtract polynomials. At this point, I think this should be reviewed for everyone. If it's not, I have office hours today from 9:30 to 11:30, so stay after class and we'll talk more about it. Okay, so now let's try multiplying some polynomials. So we'll do x squared plus 3x plus 1, and we'll multiply that times I don't know, x plus 2. We'll multiply these two polynomials together. Okay, and the thing that we need to remember about polynomial division is we need to take each term of the first polynomial and multiply it by each term of the second polynomial. Okay, so this is kind of like a FOIL process, except it can be a lot more complicated than FOIL if we have a trinomial or more terms than 3 terms in either of our polynomials. We have to make sure that we multiply each times each. So the first thing we're going to do is take x squared and multiply it by x and by 2. So we'll get 2x cubed, and we'll add, no, I'm sorry, not 2x cubed. We will get x cubed, and we will add 2x squared. Now the next thing we need to do is take 3x and multiply it by each of these two terms. We'll have 3x squared, and then we'll have plus 6x. And then lastly, we'll multiply 1 here times both of these two terms, and we'll get plus x plus 2. Okay, so that's how we multiply polynomials. Okay, we're not going to talk about dividing polynomials just yet. It becomes a little bit more complicated. Some of you may have seen long division of polynomials before, but we might have a unit on that later, I'm not sure. So we're going to hold off on dividing polynomials for now. Okay, so this is just a review of how we multiply and add and subtract polynomials. Okay, we'll do the anatomy of a monomial. I already kind of did this with the polynomial, but we'll have something like a x to the p. Something like this. This is a monomial. Okay, monomial means one term. So we've got some number a, which we call the coefficient. And we have some number p, which we call the degree. Okay, so that's and I guess that's the anatomy of a monomial. Okay. So now let's talk about foiling and factoring. In fact, we already talked about foiling because we already talked about multiplying polynomials together. So let's talk about how we factor polynomials, okay? So we know that if we FOIL something, right, if we have like x plus 3 and x plus 7, we can FOIL this. And that would give us something like x squared plus 3x plus 7x plus 21, and we would combine that to x squared plus 10x plus 21. And now we want to work on going backwards. Okay. Now there's a couple different ways of doing factoring, where we take one of these quadratic polynomials and we try to factor it. I'm going to. I'll show you the quick way that I like to do it with nice quadratics with just one being the coefficient on x. So, all right, if leading term has coefficient 1, this is how I like to do it. We'll try x squared plus, I don't know, 2x plus, Now let's do something more complicated than that. We'll do x squared plus 4x minus 5. We'll try that one. Okay, x squared plus 4x minus 5. What we want to do is find strategy. Find two numbers which sum to the middle coefficient, which is 4 for us, and multiply to the constant term. In our case, -5. Okay, so 5 is a prime number. We know that the only two things that we can multiply to get 5 are going to be 1 and 5. And we need to come up with some way that we can add or subtract 1 and 5 to make 4. Well, I think if we take 5 and we subtract 1, we should get 4. So what we really want to make -5 is going to be -1 and 5. So the way we're going to factor this is just by placing -1 here with our first term and +5 here with our second term. And remember, anytime you factor, you can always try foiling again to see if your answer was right. If we were to foil this, what would we get? We get x squared minus x plus 5x minus 5 equals x squared minus or plus 4x minus 5. Okay, so that's kind of the shortcut way for factoring these terms when we have leading coefficient 1. That's usually what I will do during class. There's another way that is a little bit more surefire. If you have something more complicated, such as, call this section grouping. If we have something more complicated like ax squared plus bx plus c, we look for numbers, two numbers, which multiply to AC, something like that. I never use grouping, so I gotta be careful. Yeah, we look for two factors. That's what I should say. Of A, C, which sum to B. Okay, so that's what we're going to do. So once we have those in hand, what we're going to do is split up this into two pieces. Alex Labrador, would you mind muting your mic? I think it's kind of on. Thanks. Okay. So what we're going to do is we're going to split this up like this, and then we're going to do a little bit of magic on each of these two terms, and we're going to anti-distribute something, hope that we get something good. So it's kind of easiest if I can just show you an example. We'll do it with this one, 16x squared minus 8x plus 1. So we need two factors of 16, which sum to -8. That's going to be -4 and -4. So next, we split the middle term. So we'll have 16x squared minus 4x minus 4x plus 1. Okay. We've got 16x squared minus 4x plus 1. And now what we're going to do is we're going to take each of these. We'll put a plus in the middle. Okay. And what we're going to try to do is take out a factor from each of these so that we can get the inside to look the same. And we're sort of in a good situation here. We think that this is going to work because we can see that 16 is 4 times 4. Well, it's -4 times -4. And we have that -4 here is going to be -4 times 1 here. So we kind of see that these things have a similar kind of ratio between the two terms here. And that's really what we're looking for here. So what we're going to do now is try to match up the inside of these two terms here. Okay, so I'm going to pull out from here. I'm going to pull out a 4x. And inside I'll have 4x minus 1 left over. And then I will add, and I want this next term to look just like my original term here. I want these two to match. So the way that I can make this right side term match 4x minus 1 would be by taking out a common factor of -1 from both -4x and 1. So I'll take out a -1. So I'll put -1 out front. And then inside, what am I left with? Just 4x minus 1. Okay, and so now I have 4x times 4x minus 1 plus -1 times 4x minus 1. And what I can do now is something that sometimes I'll refer to it as anti-distributing, okay? Anti-distributing. What I can do now is rewrite this. This looks like the result of distributing the term 4x minus 1 onto the term 4x minus 1. Right? It's like I distributed 4x onto this piece and then 1 onto this piece. That's how I would go up one level. But I'm going to do the reverse. I'm going to anti-distribute and combine these 4x and this minus 1 here into this first term. Okay, so that's how we do the grouping method. Okay, so we get 4x minus 1 times 4x minus 1. And as always, we can check our work by FOILing. We get 16x squared minus 4x plus 1 equals 16x squared minus 8x plus 1, which should be exactly what we had originally. Okay. Okay, let's see. Daphne says, could you write 4x minus 1 squared? You absolutely could write 4x minus 1 squared. That's a cleaner way to write it. You know, if I'm giving an exam or something like that, I would certainly accept either of these two answers. The one on the right is a little bit easier on the eyes, but they both say the exact same thing. So thank you for that question. Are there any other questions about how we do this grouping process for factoring? Okay, like I said, I mean, a lot of the time, students don't necessarily use this method or any method per se. They just kind of like, you know, hit their head against the wall until something works, and that's fine. And if you're really good at factoring, a lot of the time you can just kind of see it beforehand. But this is a way that you can do it that if you get stuck, you can always come back to this method, and this will work for you. Shruti says no. No to memorizing, or no to no questions, or no questions. Okay. There's one more thing we need to talk about, and that's the difference of squares. Shortcut. If we have x squared minus a squared, we can factor it as x minus a times x plus a. So for example, in fact, we can even do it with c squared x squared. We can factor that as cx minus a and cx plus a. So for example, if we had x squared minus 9, that's going to factor as x minus 3 times x plus 3. And if we had, I don't know, 16x squared minus 1, we could factor that as, you could factor that as 4x minus 1 times 4x plus 1, and so on and so forth. So this is a shortcut for when we have a difference of squares. So what I mean by a difference of squares is we want to look for a minus sign, and on either side we should have x squared. Well, that's obviously a square. And on the right side we should have something like 9, which is a perfect square. When we say perfect square, we mean it's a whole number, which is a square of another whole number. So perfect squares are things like 4, 9, 25, 16, 49. Square numbers that we can take the square root of and we get another whole number. Okay, so if we have a difference of squares, we can always factor in this way. Okay, great. So let's do a little bit of factoring practice. Let's take this one and let's try it on our own for a couple minutes, and then we'll come back as a group and talk about it, okay? So let's try this one. Okay, so let's see. Looks like some people are putting their answers in the chat. That's great. In the future, please do wait for me to call for answers so that everybody has a chance to try the problem. But I hadn't mentioned that before, so no worries. So let's talk about how we're going to factor this. So we've got a coefficient 1 here in front, so we can use the fast method if we want. We just want to look for two numbers which are going to multiply to 4 and sum to 4. Well, there's only two numbers which are going to do that. No worries, Leah. So Leah had the right idea right from the start. We can factor this as x plus 2 and x plus 2. And if we want to write it in a really clean way, we can write x plus 2 squared. So perfect answers coming in from Leah, Heidi, and Morgan. So thank you all for that. That is how we're going to factor this. And remember, if you get stuck, you can always use the grouping method. Again, here AC is going to be equal to 4, and well, B is also equal to 4. So you could split it up as something like x squared plus 2x plus 2x plus 4. And then you'd be able to sort of, you'd pull a 2 out of this term. And then you'd pull an x out of this one. Okay, so that's how you could do it using grouping. All right. One more that I want to talk about is this one here. If we've got 3x cubed minus x squared, the way we're going to factor this is by taking out a factor of what we call a GCF, greatest common factor. So we look for the largest thing which we can divide out of both of these two terms. And we can see that x squared goes into both of these terms, so we can factor this as x squared times 3x minus 1. Okay, so do be aware of how we can pull out a GCF like that. Okay. Maybe we'll do one last practice. We'll do this very last one. Looks hard. All right, so the first thing we can do, looks like we can take a greatest common factor out of all of these. What should the greatest common factor be that I can take out of all of these expressions? Seeing 3, we can definitely take 3 out, but we can take more than 3. Yeah, we can take, yeah, okay, this is so awesome. I'm so glad that you guys are all participating like this. We got so many people. Awesome. Okay. Wow, that's just, I'm thrilled. Okay. So we can take 3 out. That's true. But there's another thing which is going to go into each of these 3 terms, and that's going to be they all have a common power of x, being at least x to the power 3. Okay, some of them have more, but they all have at least x to the power 3 in here. So we can indeed take out 3x cubed out of all of this. And then we'll be left with x squared plus 4x plus 4. And great, we just factored that one. So that one's going to be 3x cubed times x plus 2 squared. Okay, so that's how we're going to factor that one. That one didn't turn out to be as hard since we had already factored x squared plus 4x plus 4 just before. Okay, so are there any questions about factoring, or is there anybody who'd like to see one more example before we move on to a different topic? Okay, well, if you want more practice, stay after class. I'll be here during office hours from 9:30 to 11:30. I don't like this activity. We're going to skip it. Okay, we're going to start talking about rational expressions. Okay, so a rational expression is a fraction where the numerator and denominator, remember that's the top and bottom of our fraction, are polynomials. For example, 3x cubed minus 27 divided by x plus 2. This is what we call a rational expression. And when we say rational, the key word here is ratio. Okay, it's more like ratio null. We don't think rational like rational thought. We think of a ratio. Okay, so when we think of ratios, we think of fractions. So a rational expression should make us think of a fractional expression. Okay, so we've got this example here to guide us. All right, so that's what a rational expression is. And we can simplify rational expressions. And the strategy is typically factor the top and the bottom. Okay, that's how we simplify rational expressions. So let's have an example. X squared plus 4x plus 4 divided by x plus 2. Okay, so if we want to simplify this rational expression, what we should do is factor the top and bottom. The bottom's already factored, and we already just factored this top expression before. We have factored it as x plus 2 times x plus 2. Keep the bottom the same. And then what we can do is we can take out a factor of x plus 2 on both the top and the bottom. And we'll get our final answer to just be x plus 2. Okay, so that's the method that we have for simplifying rational expressions. We just want to factor the top and bottom and then cancel anything that we can cancel. Okay. So let's try a couple examples. We'll try these two examples. Why don't we I'll do this first one, and then we'll try the second one on our own. And I'll have us hold our answers until everybody's had a chance to try it. So let's try the first one first. This is going to be, we can take a common factor of x cubed out of the top, and then we'll have left x plus 2. And then in the denominator, we have x plus 2. We see the same thing on top as we see on bottom, so we cancel those out, and we're just left with x cubed. Okay, that was an easy one. Now let's try the second one on your own, and I'll give you guys 1 or 2 minutes. And then we'll come back. All right, does anybody need a little bit more time? If you need more time, go ahead and raise your hand in Teams. Okay. Oh, I see one hand, I think. Needs a little bit more time then. Yep, take another minute or so. All right, let's try this one together. Let's see, first, let me see if I can have a volunteer to help me just factor the top. How can I factor the top? Let's see some answers in the chat. Any ideas on how we could factor that numerator? Let's see, x plus 2, x minus 3. Yeah, it looks like everybody's kind of got the same idea here, which is great, because that's the right way to factor it. Order doesn't matter. Remember, we're multiplying, so I'll just pick one randomly. We'll do x plus 2 and x minus 3. That's right, because 2 and negative 3 will definitely multiply to get us negative 6, and if we add 2 and negative 3, we will get negative 1, which is what we need. Okay, great. And how about the denominator? It looks like we can just take out a GCF. What should we get for the denominator here? Yeah, Morgan's got it, Leah's got it, Justin's got it, Heidi's got it. We got x squared, and then we have x minus 3. And now we can cancel a term, right? We can cancel this x minus 3 here. And then the simplest that this thing gets is x plus 2 over x squared. If you really wanted, you could split it up as x over x squared plus 2 over x squared, and that would be equal to 1 over x plus 2 over x squared. I don't know. I'm not sure that's really much more simple than this. I think this is probably where I would leave it. Okay, so that is how we are going to simplify these rational expressions. Okay, we just factor the top and bottom, and we cancel what we can cancel. Okay, are there any questions about how we simplified these? All right, then we'll use our last few minutes to talk about multiplying and dividing rational expressions. I'll just give you the idea of how we're going to do it. And then probably we'll return to this section next time to actually practice. So the way we multiply them is just straight across. So we might have something like, I don't know, x squared plus 7 divided by x minus 3 times x minus 4 divided by x cubed. Okay? The way we multiply rational expressions is the same way that we multiply fractions, right? We're going to multiply numerator by numerator and denominator by denominator, but we have to be careful when we multiply x squared plus 7 times x minus 4. We're going to have to be careful about how we write it. We're going to have to write it like this: x squared plus 7. We have to multiply the whole numerator of the first fraction by the whole numerator of the second fraction, so we should have it in parentheses. And we're going to need to be careful about how we multiply these here. We can't just multiply x squared times x and 7 times negative 4. We have to do something special. We call it foiling. So don't forget to FOIL when we multiply rational expressions. In our case, we're going to get x cubed. X cubed minus 4x squared plus 7x minus 28, all divided by x cubed, x to the 4th minus 3x cubed. Okay, so that's how we're going to multiply rational expressions. Okay. The way we divide is flip the divisor and multiply instead. For example, x minus 7 divided by x squared plus 3x plus 2. Divide that by x plus 2 over, I don't know, 3x squared minus 17. The way we're going to do this is, instead of doing division, we're going to do this thing that we have always been told is equivalent to division. We're going to multiply by the reciprocal, okay? So the divisor here is referring to the thing which is doing the dividing. So we're going to flip that. We're going to get x minus 7 over x squared plus 3x plus 2. That's just the first one rewritten. And instead of dividing by this thing, we're just going to multiply by 3x squared minus 17 divided by x plus 2. And now we know exactly what to do. We're just going to multiply straight across like before. We'll get x minus 7 times 3x squared minus 17 divided by x squared plus 3x plus 2 times x plus 2. And then we could multiply all that out by foiling if we really wanted. But this is usually, honestly, where I would stop, just because it's already in kind of the most convenient form that it could be in. In fact, it could be a little bit more convenient if we were to factor this term. But this should be just fine. Okay, so that's the end of lecture today. We're up on time. If you want to see more practice problems or some examples, or if you have some questions about other aspects of the course, then you can stay for office hours. Otherwise, have a great day. Yep, no problem. My pleasure. More info on my math lab coming today. I have finally got it set up, so I'm going to send an email later today with the code for getting it set up. Yep, no problem. Callie, yes, absolutely. You totally can. I'll be in this room hanging out until 11:30, so you can just come back and tune in whenever you feel like it. Yep. Can I do one more factoring problem? I absolutely can. Let me go back up and find one. Okay, let's try this one. Oops. Well, that's not what I wanted. Let's try this. I'll just rewrite it. X squared plus 7x plus 12. Okay, so we're going to try this last factoring problem here. So we can use one of two methods. This one, we know we've got a coefficient of 1, so we can probably figure it out without too much difficulty just by kind of going at it. But we can also use the grouping method. Do you have a preferred method?
Hey, Professor, can you please factorize 3x cubed minus x squared? I didn't understood it.
Okay, yeah, sure, I can do that right after I do this one.
Yeah, okay, sure.
Let's do this one first here. Okay, so let's try it. What do we want? We know that we have a hanging kind of 1 here, and 12. That's C and A, and
I'm
B
sorry,
here is going to be.
Professor.
Oh, hello.
My connection was unstable. I don't have a preference. I would
Okay.
prefer to go with the first one because it seems too simple to me.
Okay. Yeah, so it's a pretty simple one. So we'll do the first one. So what do we want to do? We just want to find something which two numbers. We need two numbers which multiply to and add to ... Let me ask you, what should they multiply to and add to?
Multiply to 7 and add to. May you repeat that again, teacher?
Sorry, I was just asking which numbers should the two numbers multiply to and add to?
Multiply to 7 and add to 12.
Okay, got those a little bit mixed up. We actually want to flip those.
Okay.
And here's why. I'll explain why in 1 second. We should multiply to 12 and add to 7. And here's why. Okay, if we have x plus... Okay, let's say that the two numbers that we're looking for are a and b. Okay, let's give them a name. That's all I'm doing here. If we have x plus a, and we multiply that times x plus b, where a and b are the numbers that we're kind of looking for here. If we were to FOIL this, we would get x squared plus ax plus bx plus ab. And if we were to simplify that, we would get x squared plus a plus b times x plus ab. And we want this to be equal to x squared plus 7x plus 12. Okay, so in particular, a plus b should go with 7, and a times b should go with 12. Does that make sense?
Yeah, that makes sense. Thanks, teacher.
Mm-hmm. So, okay, so let's get back to what we were doing. So we want two numbers which are going to multiply to 12 and add to 7. Okay, so what we can do is write down the number 12. And what I'm going to do now is I'm going to
3 and
write
4.
down. Yeah, it should be 3 and 4. But I want you to see the method of how I do this in my head, which is the following. In my head, I go through all of the possible pairs. Okay, so one thing that can be helpful for students is if they write down all the different pairs. You know, you can multiply 12 and 1, you can multiply 4 and 3, and you can multiply 6 and 2. Those are the ways that you can get 12. And what you should then do is look at each of these and say 12 and 1, there's no way for me to add and subtract those to get 7, so that's out. 6 and 2, I can add them to get 8, subtract to get 4 negatives of those, so that one's out. And then 4 and 3, those can make 7, so those are the ones that we should use. So we should get x plus 3 and x plus 4.
Thanks, teacher.
Yep, no problem. Does that help
Yeah,
you understand?
my problem was which number we should multiply and add it to. Thanks.
Yeah, so then hopefully this part down here at the bottom kind of helps you see why it should be the one.
Can I take a screenshot?
Yeah, of course. Do you want me to line it up for you so that you can see it like that?
Yeah, teacher. Please. Thanks.
Mm-hmm.
See you later, teacher. Thank you.
All right. So then should we do the question that Shruti had?
Yeah, Professor.
It was this one, right?
Yes.
Okay. Let me add a page.
Actually, I understood how to factorize it, but I need to get the whole thing before factorization. How did you do that? And the steps, actually. I need to know the steps for it.
For 3x cubed minus x squared. Okay.
Yes.
Okay, so it's a little bit misleading to even say that we're factoring this. It's more like we're just removing a common factor, or a GCF, I guess. I guess you could think of it as factoring. Well, in any case, here's how do I want to say this? Okay. What we are wanting to do, the goal of factoring, is to take some polynomial an x to the n plus an minus 1 x to the n minus 1 plus dot 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 plus a1 x plus a0. We want to take this expression and write it as we want to take this expression and write it as x minus c1 times x minus c2 plus times and I should put m1 here and m2 here, and then we'll put dot dot dot.
Okay.
And then we'll put x minus ck. Man, I'm getting a lot of things here to the mk. Okay, so what I'm really trying to explain here is we want to take an expression with lots of different powers of x, and we want to write it as a product of lots of different factors here. Okay, lots of different factors here. Maybe let me rewrite this in a better way. Here's how I'll write it. I think that might be a little bit too confusing. That's more general, but and typically what we write in the math world, but it might be too complicated. Let's write it as x minus c1 times x minus c2 times dot 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 times x minus cn. Okay, there should be n roots. Okay, that's what we want to write it as. So we want to take some expression which has lots of different powers of x, and we want to write it as a product of a bunch of terms which look like this, x minus a number. Okay? So one thing that we should know is that sometimes c1 is equal to 0, in which case x minus c1 is equal to x minus 0 is equal to x. And so sometimes we get something like x times x minus c2 times dot 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 times x minus cn, okay? Okay. That's just when 0 happens to be that number. Okay, so let's have an example. If we factor x squared minus 3x, what we can do is recognize that this is equal to x times x minus 3. Because then we would distribute this x onto each of these, right? So that's called taking out a common factor. Okay, we took out a common factor of x. And so we could think of this as being like x minus 0, for example, times x minus 3. So we've sort of achieved the goal. Does that make sense?
Yeah, I got that.
Okay, so whenever we're factoring something, the very first thing that we should do before we start trying to factor is look for a GCF, and we should take that out first. Okay?
Okay.
So if we want to break it down into steps, the first step is remove any GCF if applicable, meaning if we can.
Okay.
Second step is use grouping or other factoring techniques. Okay, so let's use your example, which was 3x cubed minus x squared.
Yeah.
The first thing that we want to do is remove a greatest common factor, which means that we should search for
X squared.
The most complicated thing which can be divided out of both of these two terms evenly, which, as you said, is x squared. Our GCF is going to be x squared in our case. So we take x squared out, and what we should write in these parentheses is what we get if we take these two terms and we divide them by x squared. So what should we have inside?
3x minus 1.
That's right. X squared divided by x squared is just 1.
Yeah.
And this is now fully factored.
Okay. Should I write it down, please?
I mean, it's up to you whether you want to write
Yeah,
it.
I need to. Okay, so and next is and Professor, in yesterday's lecture, can you please move to the yesterday's lecture?
Oh yeah, sure. Let me put my headphones on real quick.
Yeah, okay. Yeah, the section of union and intersection.
Oh, sure.
Yeah. Yeah. Can you scroll up more? Yeah, this. No, not this. Can you move to the starting of this lecture? Yeah, this. These values versus variables. Actually, I got late, so I don't know about this. Can you re-explain these?
Yeah,
Values
sure.
versus variables, yeah.
Yeah, no problem. So,
Okay.
a value here
Mm-hmm.
is just the word that we use in math for a number.
Okay.
Okay, so if I say a
Mhm.
value, I'm referring to a specific number. And the reason I wrote down what a value is because I wanted to explain how it's different from a variable. Okay, so a
Okay.
variable is typically like a letter which we can
Yeah.
assign possibly multiple values, and the value could change. Okay, so that's what we need to consider there. So, for example, if we solve the equation, let's do what we just did. We said x squared plus 4x plus 4. Let's set that equal to 0.
Mm-hmm.
Well, then let's not do that one. Let's do let's do 5x in the middle. X squared plus 5x plus 4. The way we would factor this is we'd write x plus 4, we'd multiply that times x plus 1, and we'd set that equal to 0. And then our answer would be that x is equal to either -4 or x is equal to -1.
Yeah.
Right? So in this case, our variable here is x. And our variable satisfies the equation if the variable takes the value -4 or the value -1. Okay, so when I talk about a value, I'm referring to a specific number that we've really kind of nailed down. And if I'm talking about a variable, then I'm talking about something whose value could potentially take many values or could change.
Okay, I got that. And can you please scroll up again?
Mm-hmm.
Yeah. What's this interval notation?
Okay. So interval notation has to do with the following. Erase this.
Okay.
Okay, so we have inequality notation where we use inequality signs. So something like 0 less than or equal to x less than 7. Okay, that's inequality notation. Interval notation is when we switch this into saying the following: x lies in the interval and we want to translate 0 less than or equal to x less than 7 into an interval. So what if we were to draw this on the number line, how would it look? We'd have 0 here, 7 here. We would put a closed dot on 0, and then we would fill in the area between 0 and 7, and then we would have an open dot on 7. Is this
Why is
familiar?
it putting a closed, why is it considering a closed dot on the 0?
It has to do with this sign is a less than or equal to sign. Okay, so what I'm trying to do on this number line here is I'm trying to fill in all of the places which are values which x can take. Okay, what this first part of this says is that x is larger than or equal to 0. Okay, so I also fill in 0 because it could possibly be 0 based on our inequalities.
Yeah, I
here.
got that. Okay.
However, we have the second part says that x is less than 7. 7, the number 7 is not less than 7. It's equal to 7, right? So that's why we don't fill in the dot on the 7. We know that x can be any number. It could be like 6.9, 6.99, 6.999, or whatever, but it can't be 7 because it has to be strictly less than that number. Does that make sense?
Yeah, it's alright.
Okay, so that's why we have the open dot and the closed dot on these guys. And now if we want to write this.
Yeah, and one more thing. What if it is like x is less than 0? Means if the sign changes in here.
So if we had x less than 0?
Yeah. What's the case in this?
We would put a open dot here and it would go to the left.
Open dot. And there's no closed dot in here in this case?
No closed dot unless we were to put something like this. In which case we'd put a closed dot here and call that -3.
Okay.
But if we don't have that, then we don't. And it's possible that we have open dot, for example. If we had this. We'd have an open dot on both sides.
Open dots on both the sides. Why? But in the previous case, it was like there's one open dot and one closed dot.
It won't always be like that. It has to do with this sign means open dot. If we have this one or this one, open. If we have less than or equal to or this one, it'll be closed.
And is it implemented everywhere in mathematics?
Can you expand on that? What do you mean by that?
In the sense that if these signs come in this union and intersection, it means that it is implemented everywhere in this section, right? The closed and the open dot thing.
Yeah, I really just drew these.
Yeah.
I really just drew these as a kind of a way to visualize what's going on. This isn't really necessarily like the number
Okay.
line drawing thing isn't necessarily like a part of the class per se. It's just a visual aid that I included. The really important thing that I want people to know is that the less than and the greater than signs here correspond to these parentheses when we're talking about interval notation, and the less than or equal to sign and the greater than or equal to sign correspond to the brackets. So the important information was that these things correspond. Okay, less than or equal to sign, you get a bracket, strictly less than sign with no equal to, we get parentheses.
Okay.
So, for example, we could translate this. Let's take a look at -3 less than x less than 0. We could translate that into interval notation by saying x lies in the interval. What should go in my blank?
I don't know. I really don't know about it.
Okay, that's okay. Let me explain how we write an interval.
Yeah.
We write two numbers signifying the start and the end of the interval. And then we should have something on the sides, which will either be a bracket or a parentheses. So on this side, we'll have parentheses or bracket. That's what's going to go in this blanket, or this blank. In this blank, we're going to have a number. In this blank, we're going to have another number. And in this blank here, we're going to have either a parentheses or a bracket.
Okay.
Okay. In our particular case, we've got -3 less than x less than 0. We're going to take the smaller number and put it on the left side. Huh?
Okay, yeah, sure. Nothing.
Smaller number goes on the left side. Larger number goes on the right side.
Okay.
And whether we use a parentheses or a bracket depends on whether these signs here are less than or equal to signs. You see that?
Yeah, I do.
So whether those are less than signs or less than or equal to signs. And what we said over here,
the ones in blue are the ones that are different.
Is that
means we need to use parentheses in both of these.
Say again?
Means that we need to use parentheses in here. We have to put parentheses.
That's right.
Okay.
It makes it the same. Right.
Yep, so that's how we would do that one.
And so because of that, I think we could combine them all together for those last three. And then this is what that would look
Okay. So, should we talk more about this interval stuff?
We can move to substations, or just completely get rid of
And now, can you tell me that the question which you asked me was x lies in the interval. So how to fill that? What's the answer for this?
This is what we just wrote.
Okay.
Yeah, this.
Yeah, I got that. Okay, yeah. Now I got that. Let me click the photograph.
And move this back over to here. Right.
Maybe that's not something. So I think all that is happening in the carrier marketing stage.
Can you please scroll up?
This is talking
Mhm.
about
How far up?
Yeah, more. Yeah, that's it. A little bit down. It flies into and then yeah. This. Okay, so in this case, what's the open and the close end?
For the purple?
Yeah, in this second and then yeah, in this interval. What's the close and the opening end?
Okay, so in this case, we were working off of the following. We had 2 less than x less than 10. So the less than sign goes with the parentheses. The less than sign goes with the parentheses. So let me ask you, should we have a on our number line here, should we have open dots or closed dots?
Open.
Open. That's right.
Yeah. I know. Open.
Yeah, we should have open because we have parentheses and strictly less than signs.
Yeah. X is and X and okay. And when do we put a bracket if we take these numbers? No. What are the numbers where we put the brackets? Can you give an example for that too?
Sure. Let's do this one. In this case, we had a less than sign on the right, so we put a parentheses on the right.
Yeah.
But we had a less than or equal to sign on the left, so we put a bracket on the left.
But on the number line, what does it mean?
On the number line, it would look like this. We'd have 3 and 5. I think you already know what should go on the right side.
Yeah, 5.
What 5, and what should it be in terms of a dot?
Open.
It should be an open dot, right?
Mm-hmm.
And now that we have a different one on the left side, we have the less than or equal to sign. What should we put on the left side where 3 is?
Bracket.
Oh,
Close dot.
yeah, that's right. Okay, so less than or equal to sign goes with closed dot. And those two things go with a bracket. Less than sign goes with an open dot, goes with parentheses.
Yeah.
Okay, and we don't mix things from these two different circles.
Mm-hmm. Okay. So it means that X is smaller or equal, no, 3 is smaller or equal to the X, right?
Hmm?
And on the other hand, X is smaller to 5.
Hmm?
Okay. X is smaller to 5. Oh, that is why it's an open dot, because x can be anything below 5.
Correct. But
No,
not 5.
yeah. Okay, okay. But not 5. Anything below 5. Okay. And 3 is the closing dot because x is equal to or larger than 3.
Mm-hmm.
Oh, I got that now. Okay, yeah. And Professor, in today's lecture, at the beginning, you taught something about journal term of polynomials. Can you scroll down to that page?
Working this morning because I got up at 8:30 and then I plugged my computer into like the power thing, and then my internet suddenly stopped working. I was like, great.
You talking about this stuff?
Yeah. Please zoom out a little bit more. Polynomials. No, I'm talking about today's lecture. Starting
Multiplying
of
polynomials?
today's lecture. It is, yeah, above that. Above this.
This was last time's lecture.
Yeah,
But
this is.
I did write this stuff here.
Yeah, maybe this is what. Okay. Yeah, okay, that will be it.
Okay.
Yes, it's done. This is all I was having.
Mm-hmm.
Yeah. Thank you so much, Professor. That will be it. And yes. Have a nice day. Thank you.
Yep, thanks, you too.